So as a part of the part one of SystemVerilog cover group for functional coverage, we had looked at overall what's the concept of the cover group, and then like what are the different components of it, and we looked at few examples, and we looked at how the coverage gets reported. Now what we will do is we have looked at overall coverage solution. Now we will dissect the cover group. Okay, so our cover group primarily consists of these three things, right? So first is it has the options, right? So we will dissect and look at each of the details of those options. What are the different options that are available? Then second, we'll dissect the cover point, okay? And then how do we define the bins for that particular cover point, and what are the ways in which I can, in a compact way, that I can define bins that we had looked up at the beginning of the session in the part one as to what does it mean to learn cover group. We had seen that we have to learn some of the ways in which we can define the bins for the cover point. Similarly, how does the cross, and mainly the how do we define the bins for the cross, right? So that we will dissect and look at it. So we look at cover point, how to manage bins for the cover point, then cross and how to manage the bins for the cross, and then we'll end the session with the more information about the option. So that is what we will look at in detail in this part 2. So we'll start with the cover point. So each cover group can contain one or more cover points. So we have already seen it, right? Even in the example that we had seen two cover points, right? One for the read write and another for the address. And cover point can cover a variable or an expression. A single variable or expression can be covered by cover point. And each cover point includes set of bins, right, which is created from either the sampled value or the value transitions. So value transition is something that we have not seen so far. We will look at them, how to define transition bins as a part of this session. And then each cover point coverage is determined by total bins hit divided by total bins, right? So this is something that if you remember, as a part of our coverage report analysis in the previous example, for example, when we had done only write, the read write cover point, which had two bins, was showing only the 50%, right? So that was the total bins hit was 1, and then the total number of bins were 2, so 1 divided by 2, it was showing 50%. So that's how the coverage gets computed for the cover point. And formally the syntax for cover point looks something like this. Cover point name. So cover point name is an important component because that's what shows up in the coverage report. That is one part. And second part is, if you intend to use a particular cover point in defining the cross, then you need to have the name. Okay, so that's why you should always give a proper name to the cover point, and then cover point itself is a keyword, and then you can give the cover point expression, which can be either an expression or a variable as well. And then there is this additional IFF condition that you can specify, condition expression. We had seen this with respect to the sampling event. The same can also be used with the cover point. So what happens is, whenever the sample gets called either implicitly or explicitly, the CP expression or the variable and the condition expression optionally, if it is provided, the square bracket, when you read in the LRM, it means optional. Okay, so if you have optionally provided this CND expression, both of them get evaluated, and then the CP expression value that we have defined in the bins increments the matching bin count only if the condition expression is true, right? So for example, I said for example, in one of the cases we had seen that we had used that TLP valid for the along with the sampling event. Now I could specify the same thing along as a condition expression for the CP as well. So if I specify it, then the bin counts will only increment not only when they are matching, but when the condition is true. Okay, so the name to the cover point is important aspect. So only when the name is specified, it can be used inside the cross, as we had mentioned. And then there can be like coverage methods that you can call on a cover point. For example, setting the options those you can do only if the name is specified. For example, if I want to set the weight for the cover point, okay, the weight can be specified at cover point level as well. So I can say the name, the handle of the cover group dot CP is the name that I have given, and then I can access this options for the CP, and then I can set this parameter called weight. Okay, so this I can do provided I have given the name CP. If I don't give it, I will not be able to do it. And then the options are of two types. Something that can be specified across all instances of a cover group, or for a particular instance of a cover group. So the type option allows us to specify across all instances. So across all instances, so when I do this, the way like cov1.cp.option.weight, it sets the weight for only one instance, cov1. Okay, but if I want, like let's say cov1 is of the type cg, and I want to set the weight for this particular cover point for all instances, right, then I can use this cg scope resolution operator, cp scope resolution operator type option dot weight. Okay, I can do this, and this is the weight that will be used when the aggregated percentage gets calculated. Okay, so for cover points used only in the cross. So sometimes what happens is that you declare few cover points only to build the cross. Okay, so in such cases you can assign the weight of those cover points to 0 because you don't want, like, anyway the cross bins will be created based on that particular cover point, so you will anyway come to know whether those type of stimulus has been exercised. Then you really don't need to have the cover point itself explicitly, right? For example, in the previous case when we had done the cross of address and the read write, like, okay, both, unless you have some special significance, if you need them to be reported explicitly, which sometimes is helpful to analyze, then the cross itself will provide all the information. Okay, so you don't really need to put the weight. You can assign the weight of the read write and the address cover point to 0 and rely only on the cross, because anyway it's implicitly providing you all the information that the read write cover point and the address cover point is providing. Okay, so as a part of this session, we have been dissecting each of the elements of cover group. So we'll continue further. So we looked at cover point. Now we'll look at the bins of the cover point. So we'll just formally define it. So bins allow user to associate the value or the set of values or the range of values or transitions with a name. Okay, so there are four things. It can be one value. It can be a set of discrete separate values. It can be a range of values that is continuous, something like, let's say 15:18, something like where 15, 16, 17, 18 are included. So range of values or transition, right? As we had seen, like that is something that we have not seen. It could be like read to write, write to read, those type of transitions, right? So how we can define various of those and then associate them with the name, right? So we will look at it, but that's what is the bins. And the bins for cover point in the SystemVerilog, there are two ways. One, it can be automatically created by SystemVerilog. Okay. Second is we can do the explicit definition using the bins construct for each of these set that we care. Any one of them we care, we can define the bins for them. And when it's automatically created by SystemVerilog, what it does is the total number of bins that gets created, or the maximum number of bins that get created automatically, is limited by auto bin max. So what happens is, like, let's say I have a 32-bit address and I have defined a cover point on that. If it creates an independent bins for all 32-bit values, right, all unique values, it will become 2 raised to 32, right, which is too many number of bins. So the way it limits is using this auto bin max. Default value of this is 64. So what it will do is it will divide them in 64 equal ranges and then create them as auto bins. So that is how it works when it creates automatically. Also, when it does it automatically, it gives this name called auto, which sort of is not very easy on eyes to read it. So it's always a good idea If at all you are taking the trouble to define a cover point, then you as well define the bins for it. Okay, and there are various ways to make the definition of bin much easier and much more compact. And as we have seen, I'm just summarizing. So a cover point bin could be a specific value or a range of values, or a group of specific values, transitions, and then hit count for the specific bin is incremented whenever the sample value matches one of the value in its set, right? So if I have multiple specific values defined, if any one of the value is matching, that particular bin will get hit. The range of values, any one of the values, the value that I am sampling falls within that range, then that particular bin gets hit. And transitions, I could be defining one or multiple transition. If that particular transition is detected, then that particular bin gets hit and the count gets incremented. Number of automatically generated bins can be controlled using this auto bin max option. We will look into more details of it as we go further in the session, but the way you set it is you either you can set option.autobinmax within your CP declaration, or external to the cover group you can say cover group name.cp name.option.autobinmax and set any number of bins. So for example, if we had an 8-bit variable, what will happen is, instead of creating like 256 bins, one for each value, you can set the auto bin max and get only those number of bins. So let's say when the auto bin max is set to 64 for a cover group instance, right, which is a default value, you will get 64 equally sized bins. So what it means is 256 divided by 64, which will be 4. So each bin will have 4 values. So you will have bins created with this type of a name that you will see auto 0 to 3, and then 4 to 7, and so on and so forth, up to auto 252 to 255. So this way automatically bins like the 64 bins will be created by the equally dividing it. Just one more example to make it clear. So if we set the auto bin max to 32, then we will get 32 equally sized bins. So 256 by 32 will become 8. So each of the bin will now contain 8 values. So it will be auto 0 to 7, and then 8 to 15, and so on and so forth, up to 248 to 255. So you'll get 32 bins. And note that automatically created bins, I think in general, all the bins, including automatically generated bins, they consider only 2 state values. If there are any sampled values that contain X or Z, those get excluded. So those are not included. So by default, you only have the 2 state values that are supported in the coverage. In some cases, what happens is that you have defined certain bins, but then you want to know if there are any values that are happening other than the bins that you have defined. Okay, so you don't know, so you are exploring. So in those cases, what you can do is you can set up a default bins, and the default bin gets associated with all the values that are not defined. And note that the final coverage calculation, the way we had seen, right, like the total number of bins hit divided by total bins for the cover point, those calculation will not include the default bin. It will not add up to that. So whether it's hit or not hit, it will not going to contribute to your coverage percentage. And default bin cannot be used in the cross. And so for a specific values, you can use default, and then we have a sequence, default sequence for the transition bin. So if you want to define the default bins for transition, you need to use the default sequence keyword, and for the specific values you can use the default. Anyway, we will be seeing examples of these. How do we specify the bins for the cover point? That's what we will look at it over here from this slide onwards. So before that, we need to understand that a cover point ultimately is trying to cover the values of a particular variable or an expression. Okay, so now what happens if I don't define any bins? So as we have seen in the previous, SystemVerilog can automatically generate the bins. So the question would be that why do I not rely on that? Okay, now let's take an example that if I have a 4-bit vector, and that 4-bit vector is representing transaction types, and there are 16 transaction types that are supported, and I run the regression and I see that I'm leaving, I'm not defining any bins, I'm leaving it to auto bins. So let's say 16 bins have been created, and then bin 14 is not getting hit. Okay, so when bin 14 is not getting hit, how do I figure out what that bin 14 represents? Whether it is IO read, IO write, mem read, mem write, I don't know anything about it, right? So then I'll have to go back to spec, figure it out and resolve it, right? So while writing the coverage itself, we should write it such that it becomes easy for the analysis. And that's where the concept of defining bins comes into play. And ultimately what the construct of defining bins is helping you with is helping you represent certain set of values or range of values, and then allowing you that whether you want to represent those as single bins or you want to represent them as multiple bins. So it's allowing you control those informations. So in a way, you can take a bunch of values, filter them on certain criteria and condition, and group them and give a name to them, so that your analysis of the coverage report becomes much simpler. That's all the bin construct is really trying to help you to accomplish. So in this slide, we'll take a look at three things. To start off with, we will have more ways of grouping values as we go further, how to filter the values such that we can group a different set of values through the bin construct. We'll continue to look at it. So we have three ways in this one to start off with the simple things. First of all, if I have a set of discrete values, okay, so the individual bins can be defined to those set of discrete values using these curly braces. Okay, so that is the first thing I can do. The second thing is, if I have range of values, and for all those range of values which are continuous, I want to give one bin, then what you need to do is you can specify that using this square bracket. The square bracket based range notation, we have been using it, right, even for the arrays and bit vectors. So we have been using that type of a syntax, but same thing has to be again put in the curly braces, right? So the curly braces is a way to define the values, and within the curly brace now you represent the range using the square brackets, and that will be on the right hand side. Okay, now with the first and the second point, what happens is you are making the correspondence of multiple values to a single bin. Now what if I have defined this set of values, but I want to create a multiple bins for that? Okay, how do I create multiple bins for that? Not by defining different bin statement, but I want to define a single bin statement and I want to divide them up into different value ranges. So how do I do that? So those you can do it by defining this square bracket and providing a number, and that number you specify on the left hand side along with the bin name. You specify that particular value. Okay, so that's how you do it. So let's look at it for each one of them using the examples. So here I have a 10-bit vector called VA. I'm representing this cover group CG, and has a default sampling event through the clock, and I'm calling a cover point over here, and this cover point is sampling this particular value V underscore A, and I'm defining a bunch of bins. Okay, so let's look at how this bunch of bins behave. So I'm defining bin A, and this bin A is made up of these three discrete values. So whenever any of the values 9, 18 or 65 occurs for this particular variable V underscore A, then the bin A will be considered as hit and the bin count will get incremented. Okay, so let's look at the second example. So I am defining bin F, and I am using this the square bracket n notation to create multiple bins. So here I want to create 4 bins for all these values. So again, in the curly braces, I am defining set of values, and one of them is a range. So I have 1 to 10 and then 11, 12, 13. So now what will happen is all these 13 values will be divided up into 4 equal ranges. So it will put 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the last remaining additional values, if it cannot divide equally, it will put it in the last bin. So now we will have 4 bins. I will have f of 0, 1, 2 and 3, and each of them will be representing this range of values. Okay, this range or a discrete set of values, right? So some of them could be discrete as well. Here I have put it 11, 12, 13, but this could have been any numbers, and they would have gotten grouped in the last bin, and any of these values happen, the corresponding bin count will be incremented. Okay, so then let's look at another example on the line 65. So here what we are saying, we are defining the square bracket to create multiple bins, but we are not telling how many should be created. It's like a dynamic array type of a notation. So in such case, what will happen is it will create a bin for every value that we have defined in this curly braces. So even when we have the range, what it will do is it will unroll this range. So in this case, what will happen, it will become 127, 128, 130, and we have certain overlap. So overlap will be ignored, and then continuation of 131, 132, 133, so on and so forth up to 135. So for each of these values, one bin will created. So total of 9 bins will be created from B0 to B8. So if you want to create a bin for every value in the set that you have specified, which could be either made up of range or the discrete values, then you don't specify any dimension over here. And if you don't specify any value over here, then it will create a bin for every value in this set of values that you have captured. Similarly, over here, I have defined 3 discrete values, and then it will create 3 bins, 1 bin per each of the value. Okay, and let's look at the last one. So in the last one, I am saying bins D equal to 1000 to dollar. Dollar means the highest value of VA, which in this case, since it's 10 bit, it can go up to 1023. So now what it will do is from 1000 to 1023, for each of the values it's going to create bin in the D. Okay, and then last one we have the bin others, which we are saying the default one that we had specified, we are using it over here. So what this one does is that any values that do not belong to this range that I have defined, okay, will be captured as a part of others, and you will be able to see them in the coverage report, but they won't be utilized for the coverage calculation. When you have range of values that you are assigning to bin, there is an additional provision to filter them. Okay, and that filtering can be done with the help of this with. Let's look at an example as to how does it work. Let's say I want to create a bin for all the values that satisfy mod 3 condition. Okay, that those are completely divisible by 3. In this range, I want to create a bin for them. So how do I do it? So I say bins mod 3, and then here I am creating optionally bin per value. This is not mandatory for the width. Okay, so this is just we are using it. It could have been without this square brackets as well, wherein all the values would have been included in a single bin. And I am using this curly braces, our regular bin definition syntax, and I am defining this range 0 to 255. Now the additional thing I'm adding is I'm saying width, and in this parenthesis I'm saying item mod 3 equal to 0, and item mod 3 equal to 0 is your regular expression, right? It contains arithmetic as well as your logical operators. Now the way this works is the width works like an iterator, or like a for loop. In a loose terms, it's just a for loop. So what it is going to do is it's going to take each of the value in this particular range and apply this expression and see if it satisfies this expression. If it satisfies, then that particular value becomes a part of this array or the range list that we are specifying, and if it is not, then it gets excluded. So this way you will be able to get all values that are mod 3. Okay, and the second use case is that you can actually use functions and you can pass the value, and if it satisfies the function, then you can be using those values. If it doesn't satisfy, you leave it. So here in this case, B would be already an array. Okay, so this has to be an array because width is an iterator, so it needs an array of values through which it can go through and apply the expression and then return only the values that satisfy the expression. Now this item term that we are using, this need not always be item. It can be any variable name that just represents the value that we are getting every time we go through the iteration, right? So that's what it is representing. So you can use any name over here, and that name will contain values one by one value that comes out from this particular range or the array that we are defining. And this concept also you can use for solving this popular problem if you want to create bins for all even numbers. Then you could be saying that item mod 2 equal to 0, and if you want to create all the odd numbers, bin containing odd numbers, and you can be saying item mod 2 not equal to 0. Okay, and the point to note is, one point that I want you to note is that all possible values evaluated at the point the cover group instance gets constructed. So here in this case, all mod 3 values are evaluated when we call the new on the cover group that contains this cover point. So bins cannot be created dynamically. Okay, dynamically meaning once the cover group is constructed, at the point of construction we can use this type of filtering mechanisms to define the bins, but once it is constructed, then that once the new call is over, we cannot change anything in the cover group construct. And that is because we have to remember that every bin value acts as a counter. So we need to allocate resources to implement that particular counter, and in order for that to happen, it has to be available at the point of construction. So far we have looked at bins that are created using either the discrete values or a range of values. Now in this one, this particular slide, we'll look at how to create transition bins. So before we jump into the flavors of it and the syntax details, let's formally define it. So a transition bin represents one or more ordered value transitions, okay, of the coverage point. Now what does an ordered value transition means is that it should be like a value 1 followed by value 2. So that is the order. And when I represent a single value transition like this, the most important point to keep in mind is that this type of a transition is hit when value 1 is followed by value 2 on successive sample points. This is a very important point. It has to be sampled on 2 successive sample points. So if I sample it twice successively, one after another, if I find value 1 and value 2, then and if I have defined a transition bin in this particular format, that value 1 and then equal to and then a greater than symbol and then value 2, then this particular bin will be hit. Okay, so that is what is important. So let's take a look at example to see some of the flavors in which we can compactly define the different transition bins. So we have this enum, and I'm not using type def, so this directly I'm declaring one variable over here. Since I'm not using type def, I have to declare all variables of this enum type over here itself on this line 112. I'm defining a cover group. I'm using an implicit sampling event called at passage of USB clock, and then inside that I'm defining a cover point on this enum data type that I have declared. And I'm not going to be looking at this one, so this one we are just covering all the states. So let's look at these 4 bins that I have boxed. Let's say this is the first one. This is a valid transitions. So valid transition bin, you see it is covering 2 transitions. Okay, so if you look at it over here, we have the first transition, right? The first transition is we have this inactive to U2 and then U0 and then back to inactive, right? This is one transition, and the second transition is inactive followed by U1 followed by another inactive. So we have these 2 transition bins that are specified, and if on successive 4 sample if I see the LTSSM state to take these values, state values, then this bin will be hit. The valid transition will be hit, and if either of these, right, so if on a 3 successive sample points I see inactive, U1 and inactive, then still the valid transition bin will be hit. Okay, now let's say another way to represent multiple transition bins compactly. So in the reset transition, what we are trying to look at is that if I was in any of these states and then some form of a link reset happened, then the state machine should go back to an inactive state. So how do I cover that? So here, if you look at it on the left hand side of my transition operator, I have a comma separated list of multiple values. So when I have written it this form, it gets expanded to like U2 followed by inactive, and then U0 followed by inactive, and U1 followed by inactive. For every one of these values gets expanded and combined with the one on the right hand side. So when any one of these three type of transitions happens on two successive clock cycle, then the reset transition bin will be hit. Okay, so then we have another one. So here you can see the repetition, and we have used this repetition even in the case of assertions. So I can represent it as inactive, and in this square bracket I am saying star of 3. This means repetition, which is equivalent to inactive followed by inactive followed by inactive, and this should be on the successive clock. So if I see this 3 on 3 consecutive clock cycles, if I see inactive and then I see U2, and then this particular bin inactive 3 will be hit. Okay, and the syntax is that you take whatever the transition item that you are referring to, and then you use this star and then provide a repeat range. Actually you can provide a range as well. Here we are showing a fixed value, but similar to what we have done in case of assertions, we can define a range as well. Then any of the range values, if it is able to match, then the corresponding bin will be considered as hit. There is also a Goto repetition. The definition is slightly different compared to what we have seen in the assertion. So here what the non-consecutive repetition does is, the Goto repetition does is it allows us to define a non-consecutive repetition, and the syntax is you say the item and then this minus and greater than equal to symbol, and then you can define the repeat range, any of the range values you can define. But the difference compared to our consecutive repetition is that intermediate transition could be any other transitions that does not contain U2. That is fine. But what we have to notice, even if it happens consecutively, still the non-consecutive Goto will be considered as hit. But if it doesn't happen consecutively, intermediately, if there are different state transition, still this particular bin will be considered as hit. We used some of these transition bin operators in the previous slide when we looked at the example. Let's quickly formally define them. So we have 4 ways in which you can capture the transition bin. You have transition with range, and the syntax looks like you can define a range list 1, and then with the equal to and greater than sign range list 2. So one example is I can specify 1, 5 with the transition of 6, 7. It will automatically create all other combinations. So it will result in 1 to 6, 1 to 7, and 5 to 6, and 5 to 7 transition. So you can define the range, and it will automatically result in all valid values, combinations getting covered. And then you have the consecutive repetition of transitions. I think these 3 operators are going to remind you what you looked at in the assertion context. So this is the consecutive repetition. The syntax will be like whatever the item that you are looking for consecutive repetition, then you can define a range or a single value, right? So if I say 3 and then I use this star and 5, then that means that the 3 repeated 5 times. So it's when I consecutively sample the cover group 5 times, and in all those 5 times, if the value was found to be 3, then that particular bin would have gotten incremented. So I can also define a range, and when I define a range, what it means is if 3 happens consecutively either 3 or 4 or 5 times, right? So any one of them, the overall bin count would get incremented. Okay, and then we have the Goto repetition. So the syntax looks like this. We have transition item with the hyphen and greater than symbol, repeat range. So you can specify a range or you can specify a single value. So if I say 3 and then if I specify Goto repetition of 3, then it's in a way a non-consecutive repetition. So any values can occur in between when I sample multiple times. Then after the it will then look for a value 3, and then any other samples can occur, and then it will look for 3, and then any other value sampling and a 3. So this way it will look for 3 occurrences in a non-consecutive way, and then the Goto repetition would be satisfied. And then we have the non-consecutive repetition, which is represented in syntax. With this syntax we say transition item equal to repeat range, and so if I say 3 and then equal to 3, it looks exactly similar to the Goto repetition, right? So now the question will come in our mind that then what's the difference between Goto repetition and the non-consecutive repetition. Is the same doubt that we even had in the assertions. The difference becomes clear when you use it with the next transition. Okay, so let's look at that in the next slide. Okay, here we look at the difference between Goto repetition versus non-consecutive repetition. So I have this sequence where I am saying the sequence of transitions over here, of course. So 1 followed by 3, and then I'm saying go to repetition of 3 and followed by 5. So here what will happen is it looks on first sample for 3, then subsequently some other values can happen, and 3 such non-consecutive repetition of 3. But at the end, the final value that I have specified 5 should happen immediately. That's what it expects. Whereas when I do the non-consecutive repetition with the same sequence, up to this point 3 it remains same, but for the last value there can be again a gap in case of non-consecutive. So it can be a gap of any number of samples. Those could be different values, and after that the 5 must take place, right? So this is how the non-consecutive repetition works. So in principle it's similar to what we saw in the assertion as well. So let's look at an example. So we have a 4-bit variable VA over here. We have defined a CG with implicit sampling. We have defined a cover point and sampling the same variable VA, and then I'm defining bin SA. Okay, so when I'm defining here, I'm using the first one is a single simple transition bin, but for the second one I am using the range transition. So I am defining also the range with the square bracket way of specifying as well. Then I'm saying 7 to 9, 10 transitioning to 11, 12. So this translates to this first one will be anyway 4, 5, 6, and then it will look at 7 to 11, 8 to 11, 9 to 11, and 10 to 11, right? So those are the 3 values we have, and then again 7, 8, 9, 10, right? Sorry, 4 values. So for all 4 values it will look for transition to 11 and 12. Okay, so resulting in the total 9 number of bins. All the 9, any one of them takes place, you can again the bin count for the SA gets incremented, very similar to the way we had done it for the value coverage bins in case of Coverpoint. Note that for the transition bins we don't have the curly braces. We don't need that. Okay, just pay attention to that. And then for the transition also you can define bin per value. The syntax remains the same, similar to your dynamic array. 2 square brackets with the without anything defined in the middle. If I specify the same thing here, it was leading to 1 bin, whereas here totally 9 bins will be created, and whenever the corresponding transition takes place, that particular bin will get incremented. Okay, and then here I am doing bin SC, which I am saying 12 with the go to operation of 3, which means is a non-consecutive repetition, and it will go to the 3. So it's kind of an unbounded sequence. So anytime 12 after any number of samples 3 happens, this particular count will get incremented. And then we had looked at default for the values of the cover point, but we had not looked at a default sequence. So here is a default sequence example. So you can say bins all other, and then when you say default sequence is applicable for the transition bins. So when none of the sequences or the transitions that you have defined as user defined bins takes place, then the all other bin over here, which is defined as a default sequence, will increment. So as we have been seeing, right, so bins allow us to compactly represent set of values, and one of the other ways in which we can accomplish that objective is using the wildcard bins. Okay, so wildcard bins, what you can do is you can put in a wildcard character, and that wildcard character can represent either 1 or 0. Any of the values it will considered as hit. Okay, that's what is a wildcard character does. And the SystemVerilog LRM allows 3 wildcard characters. So you can use X, Z, or a question mark. Okay, don't get confused that X and Z doesn't represent your 0, 1 X and Z of the logic data type. It is not that one. Okay, so it is just a character here that to represent a wildcard bin, you can use X, Z or a question mark. But to avoid confusion, I would recommend that you always use question mark. But I am talking about X or Z because in case if you see it somewhere, you don't want to get confused with the logic data types X and Z. Okay, both the constraints and the functional coverage construct, they don't support X or Z as of now. Okay, so they don't support it as of this 2023, they are not supporting it. So it is always supporting only two state values. Okay, so now here let's take a look at example. So let's say I have a 3-bit operand and I want to cover only the even values. So now what I can do is I will define this bin and I will prefix this bins keyword with a wildcard keyword, and this wildcard means that I am going to use the wildcard expression in the values that I'm going to be defining. So I'm saying bins even equal to curly braces within which I have to always put the curly braces to define the values that a particular bin can take, and I'm saying 3 tick B question mark 0, because for a even number the LSB will always be 0. So when I put these two question marks, what it translates to is that this particular bin even will be hit when the operand takes the value 0 1 0, because this is two question mark, so it can take 0 1 0, it can take 1 0 0, it can take 1 1 0, and it can also take 0 0 0. So when any of these four values occur, then this particular even bin will be hit. Okay, similarly you can also define an odd bin. Okay, so you can define an odd bin, and you can use a wildcard for defining even the transition bins. For example, here we are saying 3 tick B1 question mark 1 2 3 tick B1 question mark 0. Okay, so now this is an odd to even transition, and here if you notice we are putting a bin per value, so each of the transition will get one bin for itself. So the transitions would be it will be from 1 0 1, because this guy can take 0 or 1, right? So I have 0 and I have 1, right? So it can take both of the values, and then this on the right hand side, the middle value again can take 1 or 0, right? So here I am seeing that 0 and 1 and 0 and 1. So all these four transitions are allowed. Okay, so and for each of the transition bin gets allocated. So this way wildcard bins allow you to sort of represent multiple values or multiple value transition in a very compact way. We have been looking at how to define the set of legal bins that cover the values that you're interested, but often it can so happen that you have set up a cover point on a particular variable or expression, and there are a set of values that you really don't care. So how do you exclude those values, right? So there is a question that might come in your mind that, okay, I have a way to define the bins that I really care about, then why do I need to worry about the exclusion? So sometimes what can happen is that you are probably interested in all the values except few values, right? So and then defining all the values might be a lot of effort, so you might decide to go other way around by saying, okay, I'll define only the values that needs to be ignored. Okay, so or like let's say you have a big range, and in that there are several small holes that needs to be excluded, right? So you can have a big address range and then some smaller address ranges from that particular big address range might have to be excluded, and sometimes that might be easier to write those exclusions than to define all inclusions. Okay, so in those cases you can use this feature. So what you do is a set of values or transitions associated with a particular cover point can be excluded from the coverage by specifying them as ignore bins. So how does this work? Let's look at an example. So here I have a 6-bit variable called operand values. So it's going to take 0 to 63 values, and I have set up an implicit sampling, and I have a cover point on this particular variable, right? So now what I am saying is ignore bins, and I am saying above 20. So this particular variable can take a value from 0 to 63, and I want to ignore all the bins that are above 20. So what I'm doing, I'm saying above 20, and I'm specifying the curly braces within which I'm going to define the values, and I'm saying in the square bracket 21 colon dollar. Dollar indicates whatever is the maximum value that this particular variable can take, so which will exclude any of the bin values from 21 to 63 from being reported in the coverage report. The same concept can even be applied for transition bins. So let's say I'm defining a wildcard. So this is a legal bin I'm defining. So above 7 transitions, if you see, this is the position, this is the 4th bit position that starts from 8, right? So this particular, I'm just telling you as a part of this syntax, is nothing to do with the ignore bins, but we have all the transitions that are above 7, and then I want to ignore among them all the transitions that are odd to even. Okay, so how do I do that? I say if I add wildcard. Of course, this is a wildcard transition bin. So this, wherever you use the wildcard in the bins, then you need to specify that as a wildcard bin. Okay, this wildcard keyword needs to be used. So then you say wildcard, and then you say ignore bins, and then specify the transition that you want to capture. So here we are capturing the last bit being 1 and this last bit being 0, indicates that it is a odd to even transition that we are looking at, and the rest of the 3 bits are wildcard. They can be any values. So this can map to, let's say for example, 5 tick B01111, which will be F2 5 tick B01110, which will be E. So F to E transition is an odd to even transition which is above 7, so that particular bin gets excluded. So this way you can define ignore bins to exclude the bin values or bin ranges from the coverage report. Set of values or the transitions associated with a cover point can be marked as illegal. Okay, so what happens is that you expect certain values to never occur for a particular variable or expression in the coverage. Then you can kind of add an check for that by defining those values as illegal, by defining an illegal bins. Okay, so how it works is, let's take a look at this particular example. So we have a cover group, LSR read CG, and then we can actually specify a with function sample. Okay, so this is the way actually what you can do is you can overload the sample function. So far, like whenever we have seen the sample function, especially the explicit sample function, we were not passing any arguments to it. So you can actually overload the sample function by using this syntax saying cover group with function sample, and define the set of input parameters that you can pass, which can be used for sampling the particular variable value in your cover group implementation. Now you have multiple ways of doing it. So one way is that you can access the variables in the scope, both in the module as well as in the class that we have already seen. Second, you can pass it as an formal argument, and typically, as if you remember, we discussed that you need to pass the ref type of an argument if you want to sample that particular value. And then the third way is that to the sample you can overload the sample function saying with function sample, and pass these additional argument values. And this argument value, now next time when you call the dot sample, you need to pass that particular value. So this is how this works. Okay, anyway, so let's continue. So you are defining some option names, and then we are giving a label to the cover point, which is important. And then we are saying cover point keyword, the name that we are passing it as an argument to the sample function, we are using it over here. Here you can pass by value, there's no problem, because every time you sample you are anyway calling and passing the latest value. So you can pass by value. And then you are defining a couple of legal bins over here, and then using the illegal bins you can define the illegal bins, and we are saying invalid state and we are giving a particular value. So now what happens is whenever a 1-0 takes place, then the simulator will flag a runtime error for this particular value. With the illegal bins you can also define transition. So we are defining one invalid transition from 11 to 00. So on two successive sample function calls, if the value transition happens from 2 tick B11 to 2 tick B00, then the simulator will again report a runtime error. Okay, so that's what will happen. Generally, the general recommendation is not to rely on illegal bins for doing some checks. Okay, so you can have additional checks. In your test bench, in your checker, you should have checks to catch these values and not rely only on cover group. That's because what happens is typically in projects you don't run the tests with the functional coverage enabled all the time. So this you remember, there are two types of regressions we run. One type of regression wherein we run it only to clean up certain feature. So when you are cleaning up certain feature, you are in a mode to catch bugs. Okay, so when you are in a mode to catch bugs, you know that if you run a seeded run, many tests are going to fail. So in those cases you don't enable code coverage, you don't enable functional coverage, because if there are no passing tests, what's the point in functional coverage or code coverage, right? So in the point where you are targeting your regressions to catch the bugs, you don't enable any coverage metric. So if the functional coverage is not enabled, and if you have defined an illegal bin and you are relying on the check that the illegal bin is going to provide, then that check may not exist. Then that might lead to a false test passing false pass, right? So what you want to do is you should avoid using illegal bins, or you can use this as a sort of redundant check. In verification, always redundancy is encouraged in terms of checks, so that if by any chance one check doesn't do its job, because as code evolves, maybe we added one more condition or something which led to check getting disabled. Those things can happen. I mean, of course there are ways to prevent it, but still those can happen as a part of human error. So to catch them, if we on a critical things, if we have some level of redundancy, then it can catch it. But so illegal bins typically is not a recommended approach, but the feature itself exists. So we have to use it carefully.